Anybody knows how to get the gallery view in Zoom?
क्या पूछे सर?
गैलरी व्यू कैसे आता है इसमें?
नहीं पता सर।
Yesterday we had studied frequency response of BJT. We have seen the frequency response of BJT and FET as well. Frequency response of BJT is nothing but the curve of relation between the current gain and the frequency. Current gain and the frequency. Current gain is represented by term beta, which is equal to IC by IT, IC by IB, collector current to the base current, ratio of collector current to the base current. At lower frequency, this value IC by IB is equals to HFE. It is equal to HFE. But as the frequency increases, the value drops to HFE by root 2. As the frequency increases, this value drops to HFE by root 2. Gain bandwidth product of BJT is always constant. Gain bandwidth product is always constant, is having value. Gain bandwidth product of BJT is always constant and is having value equal to Saqib. Gain bandwidth product is having value
Unity.
unity. It is always equal to 1. It is having unity value. FET, we have seen the comparison of BJT and FET. Okay. What is the difference between BJT and FET, Neha? Neha, what is the difference between BJT and FET? Shakil, difference between BJT and FET. Maruti, yes. Sophia, what is difference between
Sir,
BJT?
BJT current control device and FET voltage control device.
BJT is current control device and FET is voltage control device. Yes, Abdul Aziz. Any other difference between BJT and FET? Afnan,
Sir, BJT has low input impedance, FET has high input impedance.
BJT has low input impedance and FET has high input impedance. Correct. Asif, you can elaborate any more differences between BJT and FET? Hashim, difference between BJT and FET?
BJT voltage controller or FET current controller.
Kanchan, Firoz, voltage gain is more in BJT or FET?
BJT voltage controller or FET current controller.
Voltage gain is higher in BJT or FET? Voltage gain.
BJT.
So voltage gain is higher in BJT. Correct. Go ahead. Family of FET.
BJT has high gain,
Yes,
FET
BJT
has
has
low gain.
high gain, FET has low gain. Family of FET. FET family consists of insulated gate FET, junction FET, and metal semiconductor FET. Metal semiconductor FET is further divided into GaAs, MOSFET, silicon MOSFET, high electron mobility transistor, indium GaAs MOSFET, indium phosphorus MOSFET. GaAs MOSFET is further segregated into single gate GaAs FET, single gate, and dual gate GaAs FET. In single gate, there are two types: low power and high power. Now we have seen metal insulated semiconductor FET, MOSFET. In MOSFET, what we do, the gate is connected to the FET using an insulation device or insulator. Generally, SiO2 is used as an insulator. If SiO2 is used as an insulator, we call it MOSFET because of SiO2. And because of this insulation layer, the junction capacitance increases. Junction capacitance increases. Due to this increase in junction capacitance, it restricts the high frequency operation of the FET. It restricts the high frequency operation of the FET. So it is operable at least, it is operable up to 1 gigahertz. It is operable up to 1 gigahertz. Next was junction FET, JFET. In JFET also we separate the gate terminal. We isolate the gate terminal from the device. But here we are not using any insulating material or any insulator. We use a technique. We are using a PN junction diode, and the gate is connected. You can see that the gate is connected to the P type of material. Now this PNN will form PN junction, gate and drain terminal. So this, when PN junction is reverse bias, there will be no current and no electron flow from to the gate terminal, because gate is connected to the P type of material. So we use a technique where we reverse bias this PN junction and gate becomes isolated from the device. Next one was metal semiconductor MOSFET. In metal semiconductor FET, Karishma, can we operate this JFET and IFET at microwave frequency? Can we operate this? Cannot operate this. You cannot operate this JFET and insulated FET at microwave frequency. Can we operate ASIM? Can we operate MOSFET at microwave frequency? Can we use MOSFET at microwave frequency? Gulfaraz, can we use MOSFET at microwave frequency?
Yes, sir. Use कर सकते हैं.
यूज कर सकते हैं. Rizwan, which type of contact we use in MOSFET? Which type of contact we construct in MOSFET? Mehrab, which type of contact we construct in MOSFET? Mubin,
Sir, metal contact.
contact. It is not metal contact. Sarifa, which type of contact we make in? Yes, Amina. Which type of contact is formed in MESFET? Yes, Akhilesh. Which type of contact we form in MESFET?
So Schottky contact.
Schottky contact. In MESFET, Schottky contact is nothing but contact between metal and semiconductor. Metal and semiconductor. Because of this contact, the junction capacitance reduces. Because of this contact, junction capacitance reduces, which allows the very high frequency operation. This makes MESFET operable at microwave frequency. The operating frequency can be increased up to 100 gigahertz. We can operate it up to 100 gigahertz. Now, FET is having two disadvantages. Due to high input impedance, the matching networks are difficult to construct. Due to high input impedance, the matching networks are difficult to construct. And second is power handling capacity is small. Power handling capacity is small. Still, we use FET at microwave frequency. Why? It is having disadvantages that it is having low power handling capacity as well as high input impedance, but still we prefer FET over BJT in microwave circuits. Reason? Inshal.
जी sir.
The FET is having disadvantages that the power handling capacity is very small as well as that it is having high input impedance. Still we prefer FET over BJT in microwave circuits. Why?
So they have low power consumption than BJT and they can be operable at higher frequencies.
It's not the answer. Why we are using FET at microwave frequency and why we are preferring over BJT?
Sir, FET has low in bandwidth. Unity है.
Can explain in relation to these two disadvantages. Power handling capacity is small high input impedance. It is having high input impedance, still I am using in microcircuit. Our handling capacity is small. You can answer in chat box. If someone knows the answer, you can answer in chat box. Yesterday I had explained this while stating disadvantages. I had explained. Still we are using it in microwave. The reason for that. Nobody remembers. Due to high input impedance, it is difficult to construct the matching networks. But at microwave frequency we use waveguides. We use for transmission. We use the transmission line is nothing but waveguide over there. Waveguide is already having high impedance. If I want to construct an amplifier after the waveguide, suppose I have used a waveguide to receive a microwave signal from the source. Now, before giving it to the receiver or to the antenna, I need to amplify it. So I will be creating an amplifier circuit, and we will be creating an amplifier circuit for which I need BJT or FET. If I will take BJT is having low input impedance, so it will not match with the impedance of the waveguide. It will not be matched with the impedance of waveguide. And we know that if impedance is mismatched in waveguide, what happens? Reflection increases. We get reflected wave, which may damage our source. So I need a device which is having high input impedance. FET is having high input impedance, therefore it becomes useful for me at microwave frequency. I can use that waveguide. I can't use a device which is having low impedance. I need a high impedance device. Therefore, it is not a disadvantage for me at microwave frequency. This has become advantage for me. Disadvantages for me to use at microwave frequency. Second, power handling capacity is small. Power handling capacity, if I talk about the general circuits which operate at 230 volt, they are at high power, because 230 volt into current, if current is 10 ampere, V into I will be the power. Therefore, they should be they should handle the high power. But at microwave frequency, they operate at millivolts. Therefore, I don't require any high power handling capacity. If it is not having high power handling capacity, then also it is useful for me at microwave frequency because they operate at millivolts. Next is construction of FET. You've seen the construction. First, we use a GaAs, a semi-insulating gallium arsenide substrate material. This is called substrate material, over which we grow up the layers, buffer layer of SiGaAs. We use an oxidation process to grow this layer, over which an N type of layer is grown. Next to that, an N plus type of layer is grown by doping, because it is having a high concentration N plus. We use doping over here, over which we make ohmic contact, and ohmic contact is metals are deposited for ohmic contact and gate for source, drain, and gate. We have made ohmic contact for source, gate, and drain. This is basic construction of FET. Last year, this subject was known as microwave and radar engine. The last module, 6th module, was based on radar, but now it has been replaced from radar to integrated circuit technology. In that integrated circuit technology, we will be studying that how they are manufactured, how these integrated circuits are manufactured, ICs are manufactured, and this FET and BJTs are manufactured. How this epitaxial process takes place to growing up the different layers. We have seen the simple cross section of this FET. It consists of GaAs, over which we have N type of layer, and doping concentration is increased to make N plus regions. Depletion region is formed below the gate terminal. Depletion region is formed below the gate terminal. VGS is always negative and VDS is positive. It is always greater than 0. GaAs MOSFET always operate at high frequency, higher than 1 gigahertz. At microwave frequency, the dimension of devices are small. Its functionality. Its functionality depends on the drain to source voltage and drain current characteristics, output characteristics. The drain current is given by IDSS into 1 minus Vg by Vt naught the whole square, where Vt is threshold voltage. It is threshold voltage over which depletion region will start forming above this threshold voltage. This characteristic is similar to output characteristics of BJT, VCE IC. Frequency response. Like in BJT, we had a frequency response. It was that basically dependent on current gain and the transition time taken by the electrons to move from emitter to collector. Here also it depends on the transition time taken by the electrons below the gate terminal to travel below the gate terminal. If L is the length of the gate terminal, and V set is the velocity of the electrons traveling below the gate terminal, then it is given by tau equals to L by V set. Transition frequency is given by F is equal to 1 by 2 pi tau. F will be equal to 1 by 2 pi tau. And transition time will be L by V set, where L is the length of the gate layer. Next is HEMT. The latest addition to the solid state device is high electron mobility transistor. HEMT or heterojunction field effect transistor. Is a MOSFET based on a heterojunction instead of simple epitaxial layer. It is nothing but a MOSFET. It is also a type of MOSFET based on heterojunction. We used here heterojunction. Like in BJT, we had made for MOSFET in insulated FET and JFET, we had used epitaxial layer, and MOSFET we had used Schottky contact. Here in HEMT we are using heterojunction. This device is an excellent candidate for microwave and millimeter wave. It is used for, the heterojunction is made purposely to operated at very high frequency, above 100 gigahertz. So it should go to millimeter wave and analog application and high-speed digital applications. Construction and operation. It has three metal contact as the gate, drain, and source. Like FET, it is also having three basic contacts are gate, drain, and source. The source and drain terminals are ohmic contact. Source and drain are basic ohmic contact. Means metals are deposited for contact of source and drain. It becomes ohmic contact. The gate contact is Schottky contact. Like in MOSFET we have used a Schottky contact. Here also in for gate we are using Schottky contact. Like metal is directly connected to semiconductor material. This is the basic construction. GAS substrate over which a GAS layer is blown up, over which N type of layer is blown up, over which N plus layer is deposited. Then metals are deposited to make the contact source, gate, and drain. This gate is directly connected to N type of GAS layer. It forms a Schottky contact. As shown in figure, the channel for the carrier is formed by simple epitaxial layer. Channel for the carrier is formed by simple epitaxial layer. In HEMT, this channel is formed by a heterojunction as shown in figure. In HEMT, this channel is formed by heterojunction. Heterojunction is nothing but this gate terminal is connected to N type, which is connected to N plus of layer. So it is called as heterojunction. The heterojunction is a junction formed by different band gap material. The N plus GS layer is higher band gap material, while doped GS is lower band gap material. Both this N type and N plus type will have different energy level. GAS, N type, and N plus type will have different energy level because it is highly concentrated. The energy band of N plus will be higher than N type of layer. In this way, we form heterojunction, where metal is connected to two semiconductors. One is having different band energy, another is having different energy level. Because of the band gap difference, the electrons from the higher band gap material N plus GS transfers to an adjacent lower gap material. Because of this energy band difference, what happens? The electrons jump from the higher energy band to the lower energy band. It will jump from N plus to N type of GS layer. At the interface on the side of GS, a very thin potential well is formed, because of which a very thin potential well is formed due to mismatch of the energy bands. The potential well is so thin that the electrons transferred in GS from a two-dimensional electron gas. The potential well is very thin, and the electron can easily transfer from N plus type to N type of GAS. Because the electrons drift in the undoped semiconductor, they are not experiencing collision with impurity ions, and therefore their mobility is higher than in doped semiconductor. The electron drift in the undoped semiconductor, they are not experiencing collision with the impurity ions, and therefore their mobility is higher than in doped semiconductors. As the electrons are moving from N plus to N type of, this is doped semiconductor. This is not doped semiconductors, pure semiconductor, pure N type of semiconductor. So here there are no large number of free electrons. In N plus we have large number of free electrons. Number of free electrons is less. Therefore, the number of collision also reduces in N type. Right? This will also be a highly doped. If it will be having N plus, this will be N double plus. Then there will be large number of electrons. Then if these electrons have entered here, they have experienced the collision with the number of electrons. But as the number of electrons is very less, there will be very less number of collision, and therefore mobility will be higher. Mobility will be higher for the electrons. This makes HEMT faster than conventional MOSFET. It makes HEMT faster than conventional MOSFET. HEMT made using INP technology are operational up to 200 megahertz. The aluminum GAS under GAS device is usually called other types of HEMTs are also possible, as well as devices with multiple heterojunction The advantage of multiple junction is increase in channel charge density and thus making device usefully power amplified. This was the operation of HEMT. Basically, it has formed a heterojunction using a gate terminal which is connected to N-type and N+ type of GS material which are having different energy levels. Because of this difference in energy levels, this heterojunction is formed over here, and the electrons jump from the higher energy level to lower energy level. They jump from N+ to N-type. As N-type is not doped and N+ types are doped with high concentration, so that number of electrons in N-type is less. Therefore, electrons after entering N-type experiences less number of collision and they are free for the movement. Therefore, mobility increases in N-type, which allows free movement of electrons and which allow it to produce large current, or it allows to freely move, which allows it to operate at high frequency. Because in high frequency we need mobility of electrons, and it should be very faster. Mobility of electrons should be very faster in microwave frequency, and here we have seen that the mobility increases, therefore it is operable at high frequency. We can operate at microwave frequency and millimeter waves as well. Functionality: from a macroscopic point of view, IV characteristic of both MESFET and HEMT are quite similar है. उसका जैसे VGS और इसका था VDS ID, दिस इज VDS ID, वैसे ही इसका भी एक्सैक्ट सेम है. HEMT का कोई डिफरेंस ये है कि ट्रांसकंडक्टेंस इज हायर. Like BJT, we have Q point. In BJT, we have Q point. Shows the quality of. In BJT, Q point defines the quality of operation of the transistor. In FET, we use transconductance as the measure of quality of function. The transconductance of HEMT is higher than FET. Transconductance of HEMT is higher than FET. This is the curve of transconductance versus VGS. This VGS is generally kept negative, 0.6, 0.4, 0.20. It increases beyond 0. Transconductance 0.2, 0.4, 0.6. HMT devices are popular due to their lower noise characteristic. Noise is very low as compared to FET, general FET. HMT have very low noise, and BJT is very noisy as compared to FET. BJT is very noisy, FET is less noisy, HMT is very low noisy as compared to FET and BJT. The gain in the BJT is lower as compared to FET, but HEMT is having the gain in HEMT is also lower as compared to FET, but it will be higher as compared to BJT. It has high gain as compared to BJT, but low as compared to FET. Just shown an example that at 5 GHz, FET has gain of nearly 20 dB, but HEMT will be having gain of 15 dB. The gain is lower as compared to FET, but it is higher as compared to BJT. Frequency response. The frequency response is similar to what we have seen in FET right now. Where L is the length of the gate. L is the length of the gate. V is the velocity. Z is the velocity of the electrons traveling through the gate. Tau is the time taken by the electrons to travel from emitter to collector. Actually, this is the time taken by electrons to move from one end to the another end of the gate terminal. The time, we know that time is equal to distance upon velocity. The tau is equal to Lg by V set. Now this velocity is directly proportional to the applied electric field. We generate electric field in FET. We apply VGS negative voltage, which generates an electric field. This velocity of electron is directly proportional to the generated electric field, which is equal to mu n into, where mu is the constant called as mobility of the electron. The constant called as mobility of the electrons. Mu n equals to E is given by VTS by Lg. Drain to source electric field generated is given by VDS, drain to source voltage, by length of the gate terminal. Therefore, tau is equal to Lg by V set. We can replace this V set by this formula mu n into VDS by Lg. Will be Lg divided by VDS by Lg. This Lg will go to the numerator, it will become Lg square by mu1 VDS. Lg square by mu1 VDS. And mu1 is mobility of electrons. Where Lg is the time taken by required for the carriers to travel under the gate. This is time taken to travel from one end to the another end of the gate terminal. L is the length of the gate. Length of the time is equal to distance upon velocity. The tau is equal to Lg by V set here. V set is directly proportional to the applied electric field because it depends on the applied gate voltage. If the gate voltage is increased, V set increases. What does it mean by increased gate voltage increased? It means because VGS is negative. You know that VGS is always negative. If I set that VGS is 10 volt, earlier VGS was 10 volt. Now I'm making VGS, I'm changing it to 15. From 10 to change to 15 volt. And what I have done with the VGS now? This Neha. Earlier VGS was 10 volt. I made it 15. What I have done with VGS? Yes. Shakil. Akib. VGS was 10 volt. I made it 15. What changes I have done? I have increased the VGS. Yes, Sophia, I have increased the VGS. Yes, you can answer in chat box. I increase the VGS or I have decreased the VGS. was using FET in a circuit. I have used a battery. From battery, I have given VGS to be minus 10 volt. Then I moved my knob and it's shown me that VGS is now 15 volts. Shown on the screen that is 15 volt. Now, what I have done, I have increased my gate to source voltage or I have decreased my gate to source voltage. Deepak? Yes, Sophia? Firdaus, what changes I have made with the VGS? I increased the VGS, I have decreased the VGS. Yes, there is one. What would you say? It is an increase in voltage or decrease in voltage?
इसका सर
VGS, if I have changed it from 10 to 15, what would you say? It is the increase in voltage or decrease in voltage?
10 to 15 the decrease in voltage.
This is decrease in voltage. I have decreased the voltage from 10 to 15 volt because it is negative. And here it is said that if we increase the voltage, if we increase the gate to source voltage, then what happens? The velocity also increases. That means if I am changing from 10, right, making it from bringing it down from 10 to 9, 8, 7, 6, 5, it means I'm increasing the gate to source voltage. And what will happen? The velocity of electron will increase. Siraj sir will continue now.
Okay, hello, Assalamu alaikum. Good morning, all of you.